Hi guys, welcome to Discrete Mathematics. I will be your professor. I'm just kidding. I'm Miss Evans and I am recording these lessons from the comfort of my home. So you may hear dogs barking, you may hear mowing, you may hear random things going on in the house. So please forgive me for that. But I just wanted to record these videos so if I am absent or you're absent or anything like that, then you will have the notes and have me teaching them to you. So today we're going to start with section 1.1a, logic statements and quantifiers. Today the pens that I will be using are red, blue, and a highlighter. So we will not need a calculator today. And so if you want to pause and get the supplies you need out, also I will have given you or sent you the fill in the blank note sheet, so make sure you have that handy. If you don't have that printed out, then you can always copy this stuff down as well. So today we're going to start with the question, why do we study mathematical logic and reasoning? And the reason we study mathematical logic and reasoning, the first reason is to learn about the careful use of language. Okay, so you have to be careful with what words you use in math or other subjects because the words you use can change the meaning of if something's true or if it's false, or if it's sometimes true or sometimes false. So we use mathematical logic and reasoning. We study that because we have to be careful with the words we use. Also, we learn the meaning of generalization. And that goes along with the same basic concept that I was talking about. Does it create just a broad statement that covers a lot of things? Okay. Also, it provides us with criteria for a valid proof. And you will learn about proofs a little bit later on. But it will give us criteria to prove things. Okay. What is a statement? Well, a statement is a sentence that is always true or always false. And as you can see, you've heard your first dog bark. That is Finley K. But not both. Okay, so what I mean by this is that a statement could be true all the time or false all the time. It doesn't have to be one or the other, but it can't be both. So if it's always true, that's fine. If it's always false, that's fine. It just can't be wishy-washy. It can't be, oh, well, sometimes it's true, sometimes it's false. That's not a statement. As long as it's firm in its belief, like of always being true or always being false, that's what makes it a statement. So let's look at some examples. Is the sentence a statement? Every square has 4 sides. Does every square have 4 sides? Is that always true or always false? Yes, it's always true. So this is a statement. Yes, it is a statement because it's always true. Okay? Pi is a rational number. Well, first we have to know what a rational number is. So let's just knock the cobwebs off and refresh our memory. So a rational number can be written as a fraction. So if it can't be written as a fraction, It is not a rational number. Okay, so pi is 3.14, blah, 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 blah. Well, I can't make that a fraction. I never can make that a fraction. So this means it's always false. So it's still a statement because it's always false. Okay, 4x is an integer. Let's come over here and write what an integer is. An integer is a whole number like 1, 2, 3, 4, 5, 6, or 0, and their opposites. So negative 1, 2, 3, 4, 5, 6, on and on and on and on. Okay, but the question is, what is x? Well, they didn't tell me. So if I put in a 2 there, yes, that becomes 8. That's an integer. But what if I put in 1/3? 4 times 1/3 is 4/3, or 1.33333. That's not a whole number. Okay, so this is wishy-washy. Okay, so this answer is no. And depending on what x is, it could be true or false. Okay, red is the best color. In my family, we really like red. Okay, we think it's one of the best colors. Okay, but you might not think it's the best color. Okay, so this one's no, because it either is or isn't. There's no, cannot be both. So everybody has to agree it is the best color or it isn't the best color. We can't have part of the population thinking it is and part of the population thinking it isn't. Okay, so that's why it's not a statement. All right, so let P of x represent this, okay? P of x is the sentence, 4x is an integer. P of x, what did we say, is not a statement because it might be true or false depending on the value of x. Okay. All right. What about P of 3? So what does it mean when you say P of 3? It was P of x, and now you see P of 3. What changed? Well, x became 3. So x is going to become 3. So in this problem, P of 3 means that we're going to do 4 times 3. That gives me 12. Is 12 an integer? Is it a whole number? Yes. This is an integer. So P of 3 is always true. So P of 3 is a statement. Okay? Now, P of 0.9. P of 0.9. So let's plug that in. And I'm going to help you out a little bit here because I told you didn't need a calculator. So 4 times 9 is 36. We would need one decimal place. So that's going to be 3.6. 3.6 is not an integer. Okay, so this is not an integer. It's never going to be an integer. Did you hear me say that? It's never going to be an integer. Okay, so P, what did I write an F for? P of 0.9 is always false, because it's not a whole number. Since it's always false, so P of 0.9 is a statement. And that's tricky for a lot of people because you think when something's true, it is something, and when it's false, it isn't something. So you've got to wrap your mind around, as long as it makes up its mind, it's either always true or always false, it's a statement. If it's wishy-washy, it's not a statement. So, for P of X, we need to be a statement. We need to clarify. How do we know if it's a statement? As long as they give me what X is, I can determine if it's true or false, and it's always going to be a statement. So we can say if a value is given for X, then it is a statement. Okay? Now, the next thing we're going to talk about is this little piece right here. Okay? For all integers X. Okay? When you add for all integers X, adding this phrase makes it a statement. So for all integers X, so as long as you plug in a whole number or its opposite in here, you're always going to get an integer. Okay? Because you told what type of number X is going to be, okay, you call that for all is called a quantifier. Okay, but this statement made it a statement because you said what kind of numbers you're going to plug in here. Okay, you said what you were plugging in instead of just being a random X. So this is called a quantifier. Okay, it gave you a quantity of numbers you're using, a quantifier. Okay, now what you're going to learn this year is we mathematicians are super lazy. We don't like to write a lot of words. Okay, this is a lot of words for us mathematicians. So we love a symbol. Okay, so anytime you see the words for all, we came up with a symbol. An upside down A means for all. Okay, and this little symbol right here, which is called a double back Z, because you have the little double lines right here, double back Z, it means set of integers. Okay, So we could actually write this sentence like this. For all integers x, for x is an integer. Now, you could also write like this, for all, and I'm not good at drawing that Z, but there you go. For all integers x, for x is an integer. Now, you can't put the symbol for here. Whoops. I really should not have put an S on that. Let's see if I can find some whiteout. You're going to want to invest in a little thing of whiteout because we use ink to take our notes in. Because this means the set of integers, the set of all integers, and here we just mean a singular integer. Okay? So, in case you're just curious, why did we use the letter Z here? Okay? Integers were studied by German mathematicians. The German word for number is Zahl. Okay, so for x and z, and I should have wrote it like that. So for all numbers x in z, sorry about that, 4x is an integer. Okay, for all x in z, that actually reads better instead of for all set of integers x. So for all x in z, 4x is an integer. Okay, so how could we write that? For all values x in the set of integers for x is an integer. Okay, so we're going to just be learning a few symbols. All right, now we're going to do another example. If you need to pause it because you write a little slower, feel free to pause me at any point, and you can rewind me and listen to it again at any point too. So example 2, for all integers x, x over 3 is an integer. Okay, so we're going to do for all x in z, x over 3 is an integer. Okay, so remember an integer is a whole number or its opposite. So if I plug in numbers here, they're saying they're going to make a whole number or its opposite every single time. Now, is that always true or always false? Okay. Then it's saying for all of these. So that's not true. Okay, give me a number that would make it false. 1, 2, 4, 5, 7, 8, 10. So what numbers do work? 3, 6, and 9, just out of the first 10 numbers. Okay, so if x is any number not divisible by 3, so if you can't divide it by 3, it will not be an integer. Okay, so now we have to decide, is it a statement? Okay, is it always true or always false? Well, we had numbers that it made it false, and then 3, 6, and 9 made it true. Okay, but it said for all integers, and we said that this is false. Okay, yes, there are some numbers that make it true, but the statement is false because all numbers don't work. So even though it seems wishy-washy, you have to deal with this first part. Okay, so this is yes because it said for all integers and that is not true. Okay. All right. If you need to listen to any of these notes again, please feel free to rewind and listen to anything. And if you have any questions, please let me know. And you do have an assignment, and that should be either given in Canvas, or a sub should give it to you, or I emailed it out to you. Thank you so much. Have a great day.